second talk by Vera Delfavero, who is a new CETA postdoc. She's going to be talking to us all about McFACTS. Populations for AGN mergers and so take it away from new users.
Thank you. And I believe that I might be missing some introduction of the mergers I'm talking about are mergers of binary black holes, which are stellar mass black holes. And we specifically have in mind these LIGO Virgo KAGRA mergers that are observed through the detection of gravitational waves. So thank you for the introduction, and I'll begin by showing some background slides on AGN. So active galactic nuclei are these supermassive black holes that have these really hot accretion disks of gas and dust circling around, and they can be in some of the largest galaxies and universe, but there are several components of an AGN that make it especially interesting when we think about possibility for observing binary black hole mergers. So typically, the formation channels for these LVK observations are split into the isolated binary channel and various dynamic channels, where the isolated binary channel has these stars that are born in a binary. Each one undergoes a supernova, they have some mass transfer, they become black holes and they merge. Whereas the dynamic mergers occur in dense stellar clusters or in the accretion disks of an active galactic nuclei. And the nuclear star cluster around an AGN might have a deeper potential well because of the supermassive black hole than a lot of the globular clusters, which allows larger and higher generation black hole mergers to occur from dynamic interactions of black holes. And for this particular model, for the code that we're using, I wanted to visualize, so I borrowed this image that there might be some initial population of black holes and around the accretion disk or an AGN, where some of them might be flying around the disk. Many of them will be trapped in the disk, but they might start with some kind of eccentric orbit. But over time, these black holes will be captured by the disk and will obtain a more circular orbit over time. And I'll look a little bit more about how they might merge in a couple of slides. But from an observational perspective, active galactic nuclei have some rather large uncertainties, as large as the font size. And one of those is that we don't really know how long an accretion disk or an episode of active galactic nuclei activity might last. So if we see in some cubic gigaparsec some number of AGN, suppose we see 50 AGN, we don't necessarily know whether there have been 50 new episodes of AGN accretion over the past 50 megayears, or whether they might have formed over the last 500 megayears, each one lasting a little bit longer. And that can be really important because the initial stellar population, including black holes of the AGN disk, can be exhausted if all of the objects in the disk merge or are ejected or form some kind of stable orbit that doesn't lead to a merger. And some other uncertainties that remain for these AGN are how large the accretion disks might be around these supermassive black holes, and how the density or opacity or other physical characteristics of these disks change as a function of distance from the supermassive black hole. And all of these assumptions can have a strong impact on the number of binary black hole mergers we might expect to see from a dynamic encounter scenario in one of these nuclear star clusters around an AGN. So we developed this code, McFACTS, which is, we assume a fixed disk model for some particular AGN galaxy, and we evolved the orbits of these stellar objects in the disk, and some of them might interact. So we might imagine that we start with somewhat eccentric black hole population that might be slowly circularized over time in the disk. Some of them might encounter each other and form loose binaries, and then additional third body interactions with other stellar objects in the disk can cause those binaries to tighten, and then potentially gas or gravitational waves might drive them towards a merger. And there's all kinds of other things that can happen with these populations that I don't have time to go into, but one of them is the potential for extreme mass ratio in spirals, where a black hole might merge with not another stellar mass black hole in the disk, but with the supermassive black hole at the center of the galaxy. And these memory events, extreme mass ratio in spirals, are really interesting to the LISA community, which is around this gravitational wave observatory that the ESA and NASA are planning to launch to observe gravitational waves from a solar orbit. With the development of this software package, we submitted, and all three of these papers have been accepted by the Astrophysical Journal. The first paper, led by Vera and Salvador Ford, was more about the code and the assumptions made for objects in the disk and the disk itself. The second paper by Harry Cook was focusing on how the mass ratio and effective spin distribution of the black hole mergers in the AGN channel changed when you vary a fiducial disk model by only turning one knob at a time. And then my paper was exploring, if we look at, say, an astrophysically motivated galaxy population, how will the binary black hole populations that we expect to observe change compared to say, assuming that all of the AGN have the same properties, supermassive black hole mass, disk model, etc. And so to start with, I looked at a number density of AGN in the universe as a function of redshift, and I split up the history of the universe into different periods. And in each period, I sampled from the galactic stellar mass function for that period of history to give a stellar mass for some population of galaxy samples. And then I inferred the supermassive black hole mass and the nuclear star cluster mass for these galaxy samples using a power law to observationally motivated studies of how supermassive black hole mass, nuclear star cluster mass depend on the galactic stellar mass. Following this, there are two families of disk model that we explore in my paper. And the first one is based on something called a Serco-Goodman disk, which is a set of profiles like opacity and density and temperature that describe how the properties of the AGN disk change as a function of distance from supermassive black hole. And several of the quantities in that disk model are defined in terms of these RG units, which are essentially scaling with the mass of the supermassive black hole directly. When you use the same Serco-Goodman disk model and you just scale it based on your supermassive black hole mass, that can lead to some interesting or problematic features of the accretion disk. And so therefore, it makes sense to scale some of the properties by the SMBH math in different ways. So that on stage right is the fixed disk model. And on the left is a disk model from a software package that we use called PAGN or KAGRA, which is based on the Serco-Goodman disk model, but has an equation of state so that when you change supermassive black hole mass, rather than just scaling everything linearly with supermassive black hole mass, you, I don't want to say simulate, but you envision why the disk model might have different properties based on these profiles and equation state. And you use a drop in the opacity curve to decide where the edge of the disk is for that. And so we split up the galaxy samples into different mass bins in order to prevent the need for an infinite number of McFACTS simulations. And first we studied how many binary black hole mergers you might expect from an AGN for a given lifetime for both disk models as a function of supermassive black hole mass. And you can see that for the fixed disk model, it seems that most of the mergers that occur might happen in that first mega year, and there might be fewer mergers for the remaining 9 mega years in that model. And for the scaled disk model, it seems that it takes longer for some of those mergers to happen. And the reason I wanted to highlight this is because if we look at the intrinsic merger rates, so the number of binary black holes that might merge in a universe like our own in an AGN disk, you can see that there's at least an order of magnitude in difference between the two families of disk models. And that depends on the AGN lifetime. And if you're wondering why, as you have a longer lifetime, you might expect to see fewer mergers, it's because you have a longer duty cycle and there's fewer new episodes of AGN activity occurring. And then we applied a detection model to figure out how many of those the LDK might observe. And we find that maybe a significant fraction of them might come from the AGN channel, or maybe not, depending on what assumptions. As with any of these population synthesis codes, which take a broad set of assumptions and evolve a population, each assumption can make a huge difference in the number of mergers that you might expect to see. But sometimes what's more telling is a density function, and so I apologize for the coordinates in this corner plot here. We're looking at 2-dimensional and 1-dimensional histograms for the properties of binary black hole mergers from one of our disk models. And this is detection weighted. And so you can see in the histograms, so color of the 2-dimensional histograms and the blue line in the 1-dimensional histograms, you can see the population predicted from the AGN. And you can see that even in, if you know these, if you don't know these coordinates, don't sweat it, because the next plot is in terms of mass ratio, the total mass of the binary, and spin magnitudes, which are a little easier to understand. And on top of this, I have plotted a point for the recent gravitational wave detection GW 231123, so that you can see that it is consistent with what we might expect from a high generation merger from an AGN disk. And there's a lot of features in here that I could spend more time going into if anybody has a question. And in the future, we're going to look more at memory populations, and what happens when we consider the influence of stars and other kinds of stellar objects in the AGN disk, as well as updated kick models from these merging black holes from the numerical relativity surrogate and some other assumptions as well. And you can see the name of each of our group members who might be leading that investigation. And so, thank you.
Yes.
Can you talk a little bit about how McFACTS handles the formation of binaries in the just from statistical purposes?
Well, I can definitely say that it does do that. So way back at the beginning, there was this model diagram. And so it's important to understand that when a dynamic encounter happens, there might be a formation of a binary. There might be the tightening of an existing binary, or you might ionize a binary and split it up into components. But I would recommend reading the first paper that was led by Vera if you want to know more about how that's handled in the code.
Is there any other environment that contributes to what is seemingly saying that the second generation black holes, less than first generation black holes, and given the big velocities, is this the only environment potential law?
So I haven't carefully studied the population as a whole, especially considering the fourth observing run. However, for GW 231123, I've looked through a lot of literature, and other formation channels are having a really difficult time producing this merger in particular, because in addition to the spin magnitudes here, it's expected to have a remnant spin close to 0.8 or 0.9, and it is very difficult to form a remnant spin. So for the merged black hole, with a near maximum spin magnitude, because it's hard for that to happen if the black holes are oriented randomly when they encounter. Additionally, its high mass suggests that kick velocity for the components might cause an escape from a globular cluster. There are other papers that have come out that I can point you to where people explore how this might happen in other formation channels, but maybe I'm a little bit biased. I think it came from this one.
Can you remind people, I mean, I guess on but like the properties of this particular, like what would the mass is?
Yeah, so each mass was pretty close to or above 100 solar masses, which places it in this apparent stability region, which is also called the upper mass gap, where it's not expected that any black holes can form from isolated evolution, just because when a star that massive undergoes a supernova explosion, it might be blown apart completely without forming a black hole, because I think of an oxygen absorption line that captures this pair production that happens in those stellar atmospheres.
Yes.
On this slide, you said that the complex topography was meaningful. That's a little bit more about that.
Yeah, so you might see here that there's different blobs in, which is what's actually the 95% contour. There's a blob near low spin and low mass, a blob closer to 0.7 and a blob closer to 0.9 in spin. And those actually correspond to the generation of the components of each merger. So the first generation mergers make up that blob that's closer to 0 spin magnitudes. The second generation merger make up those blobs that are, I don't know if you can see the mouse, but that are not quite liminal, but are present and at least maybe not distinct in the population you might observe if you're only seeing a couple of binaries, but distinct in the density function that we see here. And then the higher mode clumps might be harder to disentangle. There might be some correlations between some of these parameters, but it's not especially evident in this particular plot what those correlations might be. In some of our other papers, we have some more comments on that.
I think you mentioned that in the scaled disk model versus the fixed model, that binaries merge later. Do you have any sort of insight into why that is? Like what about the physics of the disk that's different that is driving the later merging?
Yeah. Let me see if I have a large slide. I don't. That's okay. If you want to know more about that, I recommend looking at the McFACTS 3 paper. Or come and talk to me after the talk and I can show you some plots that we maybe didn't have space for in the paper that show what those profiles and opacity and density look like at different masses.
Thank you.
Awesome. Let's thank both of our speakers again.